Hello all your sons, let's see this question of current electricity from Pathfinder. It's a MCQ question number 22-23 based on a paragraph. Question reads, a parallel plate capacitor is filled with two layers of different materials A and B as shown in the figure. On the next page, material A has a dielectric constant K1 and conductivity sigma 1. Material B has a dielectric constant K2 and conductivity sigma 2. Capacitor is connected across an ideal battery of terminal voltage V. Permittivity of free space is epsilon naught. What is electric field in the material? That is asked in the question number 22. And what is the total surface charge density on the interface material? Like here, what is the charge accumulation density here at the interface? So that was the diagram given, and sigma 1 and sigma 2 are the conductivity of these two dielectrics. When there is a conductivity given, it means that the charge leaks through the dielectric, charge is flowing through them. So this potential difference, though V is maintained, current will leak through these dielectric, and we know that even if the area of cross section is not same, the current is same across all sections. So the same current will leak through A and the same current will leak through B. The area same, so their charge density will also be the same. Current density will also be the same. So current density and electric field have a relation, and that relation is a J is equal to sigma E. J is the current density, sigma is the conductivity, and E is the electric field. So because J is same, so if in material A electric field is say E1 and in material B electric field is E2, so we can write J in material A will be sigma 1 E1 and J in material 2 would be sigma 2 E2, and that is J. J is actually not required, but that is needed for the relationship between E1 and E2. And see, what is the potential difference from here to here? The potential difference from here to here is a E1 into D1, and potential difference from here to here is E2 into D2, and that total potential difference from here to here, if we go from here, that is V. So another relation is E1 D1 plus E2 D2 is equal to V. So from these two relations we can find the E1 and E2 both. So write E1 here, D1. In place of E2 you can write sigma 1 E1 divided by sigma 2, and that is a V. Just simplify, so you will get E1 is equal to sigma 2 V divided by, how much that will be, D1 sigma 2 plus D2 sigma 1. And also if I need, I can get E2 also. So the same way you will get E2 is equal to sigma 1 V, denominator will be the same. So D1 sigma 2 plus D2 sigma 1. Let's check the option answer. Electric field in the material A is a V sigma 2, D1 sigma 2 plus D2 sigma 1. I think that was the option. V sigma 2, D1 sigma 2 plus D2 sigma 1. So option D is correct. And now the charge accumulation. So for the charge accumulation, let's go to next page. Here I take a very little Gaussian surface, just a very small distance here and a very small distance here in this region. That is my Gaussian surface. If I make a diagram in the 3 diagrams, so that Gaussian surface would be something like this. It is containing the interface, like that is the Gaussian surface, and this is the common interface, like this. So the charge that is containing is that interface. So here at this interface, electric field, this is in the A. So here electric field is EA vector, and here electric field would be EB vector, and all the four that area at those surfaces electric field will be perpendicular to area vector, so no flux would be there. And area vector at this point, area is always the outward normal, so that is SB here, and here area is SA here. So just apply Gauss law on this Gaussian surface. So we will write integration of E dot ds is equal to Q enclosed by epsilon naught. At this, suppose this area is say A, so that will be EB into A. Same direction, electric field area vector in the same direction, dot product is positive. Here the flux will be minus EA into A, Q enclosed by epsilon naught. So Q enclosed is equal to epsilon naught EA minus EB, EB minus EA, EB minus EA, and into A. So I can take A here, so that will give me the surface charge density sigma in. So epsilon naught EB minus EA, and put the EB minus EA, that here I had written E2 and E1. So this E2 minus E1 is EB minus EA, sigma 1 minus sigma 2 V divided by that whole thing. So we will get here sigma is equal to epsilon naught, let me check it again, sigma 1 minus sigma 2, sigma 1 minus sigma 2 V divided by d1 sigma 2 plus d2 sigma 1, and that is what this surface charge density and this conductivity. Don't just confuse it, these are different things. This surface charge density and these are the conductivity. So that is a sigma naught V, sigma 1 minus sigma 2, d1 sigma 2 plus d2 sigma 1. So that is option B. Thank you.